Good day everyone. I am Joseph Valencia, ECE 3201, and my topic to discuss is semiconductors. If we now turn our attention to an intrinsic semiconductor material, such as pure germanium or silicon, two types of current carriers are present. These are the electrons and the holes. The electrons are those from the top of the field valence band, which have received sufficient energy to cross the relative small forbidden band into the conduction band. The forbidden band energy gap in typical semiconductors is the order of 1 electron volt. The vacancy left by these electrons represents unfilled energy states in the valence band, and which may also move from one atom to another atom in the crystal. The vacancy is called the hole. The vacancy is called the hole, and many semiconductor properties may be described by treating the hole as if it has a positive charge E, and a mobility of Un, and a mobility of mu each, and an effective mass comparable to that of the electron. Both carriers move in an electric field, and they move in opposite directions. Hence, each contributes a component of the total current which is in the same direction as the provided by the other. The conductivity therefore is a function of both hole and electron concentration and mobilities. It's given by the formula conductivity is equal to this row represent the charge density, and this mu is the mobility. This E means it is from the electrons, and this H represent holes. For pure or intrinsic silicon, and the electrons and hole mobilities are 0.2, and the mobility from the holes is 0.25. It is for the pure silicon. And for pure germanium, it is the mobility in electrons are 0.36 and the mobility in holes are 0.37. This will give you a unit of meter square per volt seconds, and ranges from 10 to 100 times as large of those for aluminum, copper, silver, and other metallic conductors. The mobility listed above are given for temperature of 300 Kelvin. The electrons and holes concentrations depend strongly on temperature. At 300 K temperature, the electrons hole volume charges densities are 0.25 for intrinsic silicon and 3 coulomb per cubic meter for intrinsic germanium. These values give you a conductivity of 0.0035 Siemens per meter for intrinsic silicons, and a conductivity of 1.6 Siemens per meter for intrinsic germanium. As the temperature increase, the mobility will decrease, and the charge density will increase very rapidly, and as a result, the conductivity of silicon increases by 10% from 300 Kelvin to 330 Kelvin temperatures, and it will decrease by 10 as the temperature drops from 300K to 275 Kelvin temperature. Note that the conductivity of the intrinsic semiconductors increases with temperature, while that of a metallic conductor decreases with temperature. This is one of the characteristic differences between the metallic conductors and the intrinsic semiconductors. The number of charge carriers and the conductivity may both be increased dramatically by adding very small amounts of impurities. Donor materials provide additional electrons and form N-type semiconductors, while acceptors furnish extra holes and form P-type semiconductors. The process is known as doping. This is the process. And the donor concentration in silicon as low as 1 part 10 raised to 7 causes an increase in the conductivity by a factor of 10 raised to the 5. The range of values of the conductivity is extreme as we go from the best insulating materials to semiconductors and the finest conductors. In Siemens per meter, the conductivity ranges from 10 raised to the negative 17 for fused quartz and 10 raised to the negative 7 for pure plastic and 10 raised to the 8 for conductors. And roughly unity of semiconductors for almost 10 raised to 8 for metallic conductors at room temperature. These values cover the remarkably large range of some 25 orders of magnitude. So that's it. It's my end of my lesson, semiconductors. Hope you enjoy. Thanks.